So have you copied this list? I think you had copied this list also.
Yes.
So this is called lateral inversion. This is called lateral inversion. How to measure distance of object from the mirror. This is our first heading for today. So give the heading, how to measure the distance, how to measure distance of object from the mirror. How to measure the distance of object from the mirror. So when you look something in the mirror, light enters the mirror and comes back to you. So light travels some distance. So our concept is there that how much distance will appear, when you look an object inside the mirror. So write the first concept here, that the distance appeared for the image in the mirror is equal to the distance traveled by the light. How much distance light has traveled, will be the distance appeared in the mirror. Now you have to copy this thing.
Done.
So for example, look at this example. A person is reading the chart and light is coming from the chart and it is hitting the patient eye. Now the patient will feel, now the patient will feel that the light has traveled 13 meters. So the patient will feel that the chart is 13 meters in the mirror. This is the concept of distance from the mirror. You have to copy this.
Why is there two fives adding up?
Because look at the screen, look at the diagram, 5 meter forward and 5 meter backward. Actually, the 5 meter is the patient sitting from the mirror. So light will travel like the echo, like the reflection. Light travels 5 meter twice. Can you notice light
But then,
travels?
yes, I can, but is it not the same for 3 meters as well?
No, but light is not going back to the chart. Na? Patient is sitting, light will hit the patient and the journey completes. The patient, light, look at the arrows. If you travel, so you first travel 3 meter, then you travel 5 meter, and then you travel 5 meter, like this. Three meter
Okay.
should 3 meter should not come twice, because 3 meter light is not going back to the chart. Now solve this question, MCQ. Yes, answer please. How far away from the patient is the image of the chart? Travel the light. Light travel this, then this, and then this.
7.
Yes, good. 7 meter. Now give the heading laws of reflection. Number one, the incident ray, the normal, and the reflected ray all lie in the same plane. The light which is coming, coming on the screen is called incident ray. The light which is coming back from the screen is reflected ray, and the perpendicular drawn is called the normal. Perpendicular, normal means perpendicular. So you have to copy this statement.
Done.
Law number 2. This is very important. Law number 2 is very important. Mark it important. The angle of incidence is always equal to the angle of reflection.
Done.
Now look at this law. This is called incident ray, which is coming to the mirror. One ray is going backward. This is the reflected ray. And I and R. I stands for angle of incidence and R stands for angle of reflection. The two angles are equal. So you have to copy this screen.
Done.
The two angles are always equal. Angle of incidence is always equal to angle of reflection. The two angles are always equal. So whenever you compare these two angles, you will always find that the two angles are the same. The two angles means angle of reflection and angle of incidence. So update the same screen. Experiment to verify the laws of reflection. It's a very important topic. Experiment to verify the laws of reflection. This experiment has appeared many times in paper 1, paper 2, and paper 4. So this is an important topic.
I've given that.
This experiment can be conducted in two ways. One, using the pins, and second, the ray box. Pins are those common pins. Ray box is like a laser, like a torch, a narrow torch. You have to copy this.
Done.
Now look at this famous apparatus. We have a wooden board and a white sheet of paper, and I have placed a mirror with a wooden peg, and I have placed 4 pins. First, I will put 2 pins, and then I will put two more pins. This is the real appearance of the apparatus. It's a mirror. There are 4 pins to be installed. First, we put 2 pins. Then looking in the mirror, we have to put 4 pins, total 4 pins. Look, this is the image. Looking in the mirror, we have to put 2 more pins, and then we remove the pins, join the dots, and we measure angle I and angle R. The two angles are always equal. So you have to copy this screen now.
And
So now look at this screen, and this is a mirror, and we have to look in the mirror, and then we remove the pins. So right under it, take a wooden board, place a white sheet of paper on it, take a wooden board, place a white sheet of paper on it, take a wooden board, place a white sheet of paper on it, place a mirror in vertical position, position.
but the mirror here is like in horizontal position.
No, actually the mirror is vertical, like the mirror in our houses. When we stand in front of the mirror, we will call it a vertical mirror, na? Because the board
Yes,
is,
but this one looks horizontal.
but it's not a, look at this screen, na? We can't make it 3D in our normal diagrams, but look at this screen. It is vertical. It's a vertical mirror like this. Place the mirror vertically place a mirror vertically, outline the mirror by a sharp pencil, outline the mirror by a sharp pencil place two pins P1 and P2 as shown.
Place the
Place two pins. Place two pins P1 and P2 place two pins P1 and P2 as shown. As shown. Looking in the mirror. Looking in the mirror. Place two more pins. Looking in the mirror. Place two more pins P3 and P4. Two more pins P3 and P4 such that all the four pins appear to be in a straight line. Such that all the four pins appear to be in a straight line. Look at this diagram. Such that all the four pins appear to be in a straight line. Now remove the pins. Now remove the pins. Now remove the pins and join their positions. Now remove the pins and join their positions by a sharp line. Now remove the pins and join their position by a sharp line. Then copy this diagram. Remember, normal is a perpendicular.
done. Done. Is it bright lamp? I've written the law of refraction before. Refraction. Done. Done. Done.
Have you copied it? Zainab, can you hear me?
Yes.
Have you copied it?
Yes.
Now, if you are traveling denser to lighter, the formula will flip. You have to copy this.
I've copied it.
When light is traveling from lighter to denser, you might remember this sheet. We have copied it when we were discussing water waves. The velocity changes, the speed changes, wavelength changes, frequency does not change. Frequency is something which never changes. We discussed this and we did some MCQ also on this concept. There is no change in frequency. Now, if light is traveling from denser to lighter, it is reversed. Light is bending away from the normal. Formula will change. Light will be, now the light is traveling from denser to lighter. You can notice the wavelength is increasing. So you have to copy this screen. Let me know once you have copied it.
Alphabet.
Light is traveling from denser to lighter. It is a reverse function. Now give the heading. Just observe this concept that we have studied two things. One is called reflection and one is called refraction. They are slightly different in listening. When light comes back, it is called reflection. And when light goes in, it is called refraction. So when light comes back, when light rebounds, it is called reflection. And when light goes in, it is called refraction. So there are two things. One is called reflection and second is called refraction. Experiment to show refraction of light. Give this heading. This is an important experiment. It has appeared many times in paper 2, paper 3. We have a wooden board and we have placed a white sheet of paper on it. We have a wooden board and we have a white sheet of paper on it. I have placed a glass block. I have placed a glass block on the paper and two pins P1, P2, and then two pins P3, P4. This is an experiment and I show you this so you can understand how this experiment is conducted. Look at this quick experiment. First, you put two pins in front of the glass block. So you put two more pins such that all the four pins appear to be in a straight line. Look, all the four pins are apparently in a straight line. So after giving the heading, you have to copy this screen. I'm just coming, copy this screen. Let me know once you have copied it.
I've copied.
Okay. You have to write under it that take a wooden board. Take a wooden board, place a white sheet of paper on it. Take a wooden board, place a white sheet of paper on it. Place a glass block. Place a glass block. Outline it by a pencil. Outline it with a pencil. Mark two pins P1 and P2. Mark two pins P1 and P2. Looking in the glass block, looking in the glass block, mark two more pins P3 and P4. Mark two more pins P3 and P4. Remove the pins and the block. Remove the pins and the block. Remove the pins and the block. Join the positions by sharp pencil. Join the position by a sharp pencil. Then you have to copy this diagram, this screen. Now update the same diagram, draw the normal, mark the arrows.
Done.
Now the lines should be parallel. P1, P2 should be parallel to P3, P4, and the ratio is constant. You have to copy this. Okay, have you copied it?
Yes.
So this is the experiment for that. As I mentioned when we were doing the chapter on transverse waves, if the light enters at 90 degree, it does not bend. It does not bend, it goes straight when light enters at 90 degree. Now, ray box we have discussed just now. It is a type of laser beam, and if you use a ray box, you can avoid the use of pins. Look at this diagram. The ray itself is visible, so you do not need any type of pins. You have to give the heading refraction through a semicircular or plastic block. Look at this screen. Light is entering at 90 degree. It does not bend. It's a glass block, semicircular. Light is bending as the light leaves the block. You have to copy this whole screen neatly. Need a ruler and pencil. Copy it. I'm just coming. Copy this. Have you copied it?
Yeah.
Now, we had discussed in our previous class refraction from a prism. This is called a prism. When light passes through a prism, it refracts twice. First is called the incident ray and the second is called emergent ray. I hope you remember that. There was also a concept called angle of deviation. Now, this is a similar experiment. We have placed a prism in the center and I have put two pins, P1, P2. This is not an important experiment. This is not an important experiment, but it makes a concept of that wooden board experiment. We put two pins, P1, P2. Then we put two more pins, P3, P4, such that all the four pins appear to be in a straight line.
Refraction through a prism. A prism is a piece of glass or any other transparent material bounded by two triangular and three rectangular surfaces. One of the rectangular surfaces, BCFE, is called the base of the prism. The other two inclined surfaces, ABED and ACFD, are known as the refracting surfaces. The line along which the refracting surfaces meet is called the refracting edge of the prism. The angle between two refracting surfaces is called the angle of the prism. Any section of the prism perpendicular to the refracting edge is called the principal section of the prism. It was Sir Isaac Newton who first observed that when a beam of white light or sunlight is refracted by a glass prism, it splits into 7 different colors. This shows that white light is composed of 7 different colors, namely red, orange, yellow, green, blue, indigo, and violet. This phenomenon by which a ray of light splits into its constituent colors when passed through a transparent medium is known as dispersion. The band of colors obtained due to the dispersion of light is called the spectrum. This visible spectrum has wavelengths ranging from 0.4 microns to 0.7 microns. Red light has a longer wavelength than violet light. Let us now trace the path of light through a prism. Place a prism on a white sheet of paper with a triangular face on the sheet and trace its boundary A, B, C. Fix two pins, T and S, on one side. Place the prism on the boundary A, B, C. Looking through the other side, fix two more pins, Q and R, in such a way that all the four pins appear to be in the same line. Remove the pins and mark their positions. Join TS and RQ and extend them to meet the faces of the prism at P and O respectively. Join PO. TP represents the incident ray. PO represents the refracted ray. And OR represents the emergent ray which is bent towards the base. Let PN and ON be the normal at the points P and O respectively. And let I be the angle of incidence and R the angle of refraction. If the incident ray TP is extended forward and the emergent ray RO backwards, they meet at M, forming the angle OML. Measure the angle OML. This angle is called the angle of deviation. Angle of deviation is the angle through which an incident ray deviates. Repeat this for different values of angle of incidence. Here is an interactive exercise on dispersion. Explore.
Give the heading critical angle. Now, consider a ray of light. Consider a ray of light which is traveling from denser to lighter. So, give the heading critical angle and write under it consider a ray of light consider a ray of light traveling from denser to lighter medium. When it is moving, when it is bending, when it is moving from denser to lighter, it bends away from the normal. You have to copy this screen. Have you copied it? Yes.
Yes.
Now look at this screen. Light is moving from denser to lighter. It is bending away from the normal. If I increase the angle of incidence, angle of refraction also increases. Look at this screen. When I have increased angle of incidence, angle of refraction also increases. Now, if the angle of incidence matches with, if the angle of refraction becomes 90°, the angle of incidence is called critical angle. So right under it, if angle I if angle I is increased, angle R also increases. Look at this, angle I increases, angle R also increases. So a point will come when angle R becomes 90. Now right under it, at a certain angle I, angle R at a certain angle of incidence, angle R becomes 90°. This angle I is called critical angle. So what is critical angle? Critical angle is the angle of incidence for which angle of refraction becomes 90°. You have to copy this. Have you copied it?
Yes.
Now this is called critical angle. Angle I is equal to angle C and angle R is 90°. This is called critical angle. So you have to copy this screen, copy it, and I'm just coming, copy this screen. Have you copied it?
Yes.
This is called critical angle. Now, there is a small derivation. When you are traveling denser to lighter, the formula is sine R upon sine I. Angle I is equal to angle C. So when angle R is 90, sine 90 in calculator is 1. Or when you move forward, you can get a formula n is equal to 1 upon sine C. So give a side heading, give a side heading derivation. This is actually a small derivation which is used to show how we can find the formula for the critical angle. The formula for critical angle is n is equal to 1 upon sine C. This is the formula for critical angle. So you have to copy this derivation.
Done.
Now, for example, the most common question is air to glass. Now, this is an example how we solve this formula. So copy this example now.
Done.
Now, you need to use a calculator. And you have to use a calculator. So in degree mode, you can solve and get the value for the critical angle.
Done.
Now give the heading total internal reflection. This is an important topic. Now, what is total internal reflection? If the angle of incident exceeds the critical angle, light will come back in the same medium, and this is called total internal reflection. The example, for example, you are sitting in the front seat of a car, the glass of the car is transparent. Something is on the dashboard of the car, you can see its image, but how come a transparent screen can produce an image? It means the light is coming back. This is called total internal reflection. When the angle of incidence exceeds critical angle, light comes back in the same medium. This is called total internal reflection. You have to copy this screen.
Then
This phenomena is called photoelectric effect. I'm sorry, this phenomenon is called total internal reflection. This happens when light is traveling from denser to lighter and angle I is greater than angle C. Remember, in this chapter, I means incidence angle and C means critical angle. You have to copy this. Have you copied it?
Done.
Okay. Now, this is called total internal reflection. Light bounces back. Light bounces back in the same medium. The common examples are prism, optic fiber. You have to give the heading. Examples of total internal reflection. Number one, prism. Number two, optic fiber. You must have heard about its name. That is in telecommunication. Copy this list. Have you copied the list?
Yes.
So prism we have discussed before also. Look at this prism. When light enters at 90 degree, when light enters at 90 degree, it does not bend. When light enters at 90 degree, it does not bend. Here at position Q, why the light is going down, why the light is not coming here in the question mark side? Why? Because the issue is the incident angle. The angle of incidence is greater than 42. As the angle of incidence is greater than 42, it means light will be internally reflected. It won't come out from the side of the prism. So you have to give a side heading, prism. You have to copy this diagram neatly. You have to copy this diagram. I'm just coming. You have to copy this diagram neatly. Have you copied it?
Yes.
Good. So this is called total internal reflection. Only a small portion of lenses drawing is left, and